Hello everyone and welcome back to Networks class. So last time in class we discussed the A-star algorithm for finding shortest paths. And this algorithm allowed us to be very efficient by being able to give the algorithm a sense of direction. And in this way, it wouldn't have to waste a lot of work by looking at parts of the graph that were far away from our destination node, and it could just focus its efforts in going closer to the destination node. So the plan for today is to go over homework 1. So this was the homework on search algorithms. And then when we get done with that, we'll talk about unimodular constraint matrices. Now, if you remember from a few weeks ago in class, when we discussed the shortest path linear program, we wrote it with some integer constraints on the bottom. And then we said there's some magic that lets us drop these integer constraints and just substitute it for non-negativity constraints. And so today we're going to go back and cover what exactly that magic is. And the magic comes from this unimodular constraint matrix property. But let's begin by going over homework 1. So the first couple of homework questions 1 and 2 were just to give you practice with running different search algorithms. Except they did have kind of a small takeaway message from them, which is that the search trees from a search algorithm are not unique. So we could get a totally different search tree depending on which white successor you choose to process first. And so we got a different search tree in class than you got on your homework assignments. Number 3, the question is, what's the running time of BFS if the input graph is stored as a dense adjacency matrix? Well, if you remember, our runtime computations look something like this. So O of number of nodes times the work per node plus number of edges times the work per edge. And so if the graph is stored as a dense adjacency matrix, the successors operation that used to be very fast, that used to be O of 1, now would take O of n time for successors. And so the running time would be O of n times n plus m times 1. So this second term comes from the edges, and this first term comes from the nodes. And we know that m is always less than n squared, so that gives us a total running time of O of n squared. So that was number 3. The running time is O of n squared. So number 4 was probably the first more interesting problem on the homework assignment. So this is the one where you're given an infinite supply of pennies, but you're dropped in the middle of a maze and you need to find your way out. And the question is, how do you get out? So the basic idea is, of course, to use the pennies to mark white, gray, or black nodes. So whenever we get to an intersection, we can mark it white, gray, or black, depending if we have 0 pennies there, 1 penny, or 2 pennies, say. But probably more importantly, the question is, which search algorithm would you use to get out? And one is a lot better than the other. So suppose that we decided to use BFS. What would happen? Suppose that we get dropped here, and somehow we manage to run BFS for a while. So this entire section would be black nodes. This periphery would be gray nodes. And outside the periphery would be some white nodes. So as we're running BFS, suppose that currently we're on this node right here. And so we process it. It's no longer gray, now it becomes black. And we have to now go to the next gray node to process. But that next gray node might be kind of clear across this entire section of maze that we've all marked with black nodes. And so we might get lost in our own markings as we're moving from one gray node to another for BFS. On the other hand, if we try to use DFS, DFS always maintains a path from S to the current node where you are. And so it's very easy to either move forward or backtrack one and sort of head in another direction. And so DFS here is the clear winner, and BFS wouldn't be a good idea because you could potentially get lost in the maze. So definitely use DFS to get out of the maze using the pennies. So the next question we had was this question about professional wrestlers. So we're given a graph that looks something like this. So each wrestler is a node. And rivalries between wrestlers are edges. And we want to divide the wrestlers into good guys and bad guys. And the basic idea is to just do search. And then every time you see a white successor, give the successor an opposite label of its parent. Of course, the first node you can start arbitrarily as good or bad. So first node arbitrarily good or bad, whichever you choose, it doesn't matter. So for example, here we start at HH. We label that guy good. He has two white successors, and so those we can label bad. And then we process one of them. Let's say this one. There's one white successor, so we label that good. So the next question is, how do you know if you can't do this? So if the graph looked like this, then we wouldn't be able to do the labeling of good guys and bad guys. So that's because we would start with the first node as good. It has 3 white successors. This one would be bad, bad, bad. And then we process one of the white successors, and we see an edge to a node that's already labeled with the same label as this guy. So we can add a third part here that if you see a gray or black successor with the same label, we know the graph can't be separated into good and bad. So you may have figured out after looking at this problem long enough that the key property here, the thing that makes a graph not be able to be separated into good and bad sides, is an odd length cycle. An odd length cycle means we can't separate the graph. So for example, in this graph right here, here's an odd length cycle. It's a cycle of length 3, and we couldn't separate that graph. And similarly, if we had a cycle of length 5, say, there would be no way to separate this graph into good and bad parts. But really, this problem has to do something with something quite fundamental, which is called bipartite graphs. So a graph is bipartite if we can separate the vertices into 2 parts, let's say A and B, such that all the edges go between A and B. So in terms of a picture, it would look something like this. Here is part A, here is part B. There would be some nodes in part A and some nodes in part B. But all of the edges kind of go between these parts. And there's no edges inside of B and no edges inside of A. So bipartite graphs are very important. They come up in all kinds of applications. So for example, one application would be matching people to jobs, where one side of the graph here would be people, another side of the graph would be jobs, and you could put an edge if that person is eligible for that job, but no edges between people or no edges between jobs. Oftentimes, problems are much easier to solve on bipartite graphs than they are on non-bipartite graphs. So you'll find special algorithms about bipartite graphs. And this property even comes up in other classes. So if you've studied Markov chains before and you've talked about the stationary distribution of a Markov chain after you do many rounds of stepping on the Markov chain, it turns out that if a Markov chain is bipartite, it has no stationary distribution because if the distribution starts at A and the next turn it'll be at B and then the next turn it'll be at A and then at B. And so if it's bipartite, you just get this bouncing back and forth effect without any stationarity. So that comes up in other classes as well. But the point is that in this professional wrestler problem, you're actually, when you label the wrestlers as good guys and bad guys, what you're actually doing is you're creating this division of A and B to try to see if the graph is bipartite. So we started out with this example, and at the beginning it may not look like this is a bipartite graph. So here's A, B, C, D maybe. But if we label this as good, this as bad, bad, good, this tells us how to construct a picture from this graph that looks like this picture above. So we would do this by making A and D be on one side and making B and C be on another side. And now all of the edges here would go across. So A goes to B and A would go to C, and similarly like that. So we turn this graph to look like this bipartite picture that we saw above. So that's the basic idea of the professional wrestler problem. It's really about bipartite graphs and identifying whether graphs are bipartite. So let's talk about the next problem. So this is a problem where you're given a directed acyclic graph, and you have to count the number of paths from S to T. So let's just draw an example here to make things concrete. So here's an example directed acyclic graph. Maybe something like this. And let's say this is S right here, and let's say this is T. And we want to count the number of paths from S to T. The basic idea of this is to do an algorithm that looks very much like the DAG shortest path algorithm. So what we're going to do is just process the nodes left to right. Let's see. Every node left of S, we're going to label with a 0. We're going to label S with 1. And we're going to label each node right of S with the sum of the labels on its predecessors. So let's see how this works, and then as we're doing this, we'll figure out what it actually means. So here it said label every node left of S with a 0, label S with a 1, And then for every node to the right of S, we're going to label it with the sum of its predecessors. So basically what these numbers mean are the number of paths starting at S and ending at that node. So there's 0 paths starting at S that can end at this node because it's to the left of S. There's 1 path starting at S that ends at S, and you can think of that as just the empty path. So how many paths starting at S that end at this node? Well, it's just one. It's just this edge. And one way to think about it is, well, the path could end at this edge, but then you have to get to this node, and there's one way of getting to this node. So that's why we're going to label this node with 1. So what about this next node? Well, how many paths start at S and end here? Well, the path could end with this edge, in which case we'd have to get here, and there's one way of getting to this node. So we're getting a 1 from this edge, and we're getting another 1 from this edge because the path could end with this edge, and there was one way of getting to the node before that. So we have a label of 2 for that node. For this node, there's 3 edges coming into it. So a path starting at S and ending at this node could end with this edge, in which case you'd have to get here, and there's 2 ways of getting here. Could end with this edge, and there's one way of getting to that predecessor. Or it could end with this edge, and there's one way of getting there. And so the label on this node is going to be 4, which is the sum of all the labels on these predecessors. And then finally, T, there's 2 ways, 2 edges coming into T. So a path that ends at T could end at this edge, in which case you'd have to get to this node first, and there's 4 ways of doing that. Or it could end at this edge, which means you have to get to this node first, and there's 2 ways of doing that. So 6 total ways of getting to T. So that's the basic idea for this algorithm. And these numbers here mean the number of paths starting at S and getting to T. So the answer for the problem, the number of paths from... So every node actually gets labeled with the number of paths starting at S. So the number of paths starting at S and ending at S is 1. The number of paths starting at S and ending at this node is 1. Starting at S and ending at this node is 2. Ending at this node is 4. And then ending at T is 6. But the answer that we wanted is 6. That's how many paths start at S and go to T. But there's an entirely different way of doing this, of answering this problem. So it works very similarly to this. So let's just copy this graph to see how that would work. So here's our graph again. And before, when we did this before, we processed the nodes left to right. But now let's process the nodes right to left. So we're going to process the nodes right to left. And now instead of labeling the nodes with the number of paths starting at S and ending at the node, we're going to label them with the number of paths that that node has to T. So anything to the right of T, we're going to label with 0. We're going to label T with 1. And label every node to the left of T with the sum of the labels on its successors. So let's see how this would work. So T gets labeled with a 1. This node has only one successor, and it would get labeled with the sum of the labels on its successor, so that's a 1. And again, that's because we're trying to count the number of paths to T. So the path could start at this edge, but then it would have to get to t from here, and there's only one way of doing that. So what about this node? So a path to t could start with this edge, and there's one way of getting to t from there. Or it could start with this edge, and there's one way of getting to t from there, so that would get a 2. This next node, a path to t could start with this edge or with this edge, and the top edge here gives us two possible completions to t, and the bottom edge gives us one possible completion to t. So that node gets labeled with a 3. And then let's see, what about S? So S has 3 edges going out of it. So with this edge, a path starting here would have 3 completions to t. With this edge, a path starting with that edge would have 2 completions to t. And with this edge, a path starting with the edge would have 1 completion to t. So 6 possible paths from S to t total. And then this last node would get labeled with just 6 plus 3, so we'll get labeled with 9. So hopefully this 6 now, that's a label on S, which should be counting the number of paths from S to t, is the same as the 6 that we got earlier, which now counted the paths from S to t, but in a different way. But of course, the nodes in between here are going to have very different labels in the two different algorithms, because these labels now mean the number of paths to t. Whereas the previous labels for the previous algorithm meant the number of paths starting at S and ending at that node. But both of these algorithms work, and both of these algorithms really work almost exactly the same as the DAG shortest path algorithm, because for both of these algorithms, the first step was to just topologically sort the graph. And after that, we just process the nodes in one direction, either left to right or right to left. Except in DAG shortest path, over here, instead of doing sums, we did minimums. So in DAG shortest path, this was a minimum, where we were looking at the minimums over the predecessors or minimums over the successors. You know, we can go back and look at the details, but the basic high-level point of view is that instead of doing a sum, there we were doing a minimum, but it's really the exact same algorithm. So that's the idea behind problem 6. So let's discuss the next problem, problem 7. So this was the 15 puzzle problem. So the first part of this is how would you model this as a graph? And the basic idea is to make every board state, a node. So here's a simple 15 puzzle, or a simple puzzle. So this is one board state, and here's another board state. And then each action is going to define an edge. So for example, to get from here to here, what we did was we slide 2 down. And what we did from there to there was we slide 2 up. And you can imagine that you can continue and build the rest of the graph this way. But the basic idea is that we have this gigantic graph of states and actions, and we have our starting state right here, and somewhere here we have the goal state. And so if you want to solve the puzzle with a minimum number of moves, you could do something like BFS, and BFS is going to give us the shortest paths in terms of number of moves from the start to the goal. So when BFS finds the goal, we know that we can solve the problem. And the path in the search tree tells us exactly what tiles to slide where. But of course, if you try to do the 15 puzzle like this, you're going to have an enormous number of states. You're going to have something like 16 factorial states, because that's how many board positions there are. So in reality, you would never really go about even trying to create this graph. But you can do it. So for example, you can, instead of constructing the graph, just write a function that gives you the successors of a given node. And that's very easy to do because, if you give me a board position, we can immediately return what are the four maximum possible successors, because that just involves sliding the one tile around. The other thing that we have to do is we have to remember the past board positions that we've seen. And so you could try to do that in something like a hash table or something like that. But the final thing is, even if we do all these tricks where we don't construct the whole graph, BFS actually explores too much of the graph because it's doing these concentric circles. And so if you really wanted to solve the 15 puzzle using one of these algorithms, you would have to use A star, in which case you need some kind of estimate function. So the estimate function here would be estimating how many moves it takes us to get to the goal state. And here's some kind of reasonable estimate functions, like the number of tiles that are out of place. Or another very reasonable estimate function that's also an underestimate is the following. So imagine here we have a board position, and that tile 1 is at the bottom, and we know we want it to be at the top. So how many moves do I need to just move tile 1 up here? Well, it's equal to what people call the Manhattan distance, which is just the distance sort of first horizontally and then vertically of getting to the desired spot. So another estimate function is the sum of Manhattan distances of each tile from its desired position. So with something like this, you would now have a direction for your algorithm in which to search, and you could just run A star, and it would sort of concentrate its search efforts in heading towards the goal. So that's the basic idea of the 15 puzzle. But probably the most important thing to learn about it is this idea, this dynamic programming idea of having the states be nodes and having actions define edges. So let's move on to the next problem, which was this problem where you're given a graph with some integer edge lengths. And you want to solve the shortest path problem, but you can only use BFS. Well, the basic idea is to just split up all of these edges by adding fake nodes. So here's some fake nodes that I've added in between. I can add 999 fake nodes, which would make this one edge now have 1,000 segments total. And so running BFS on here would give me the shortest path exactly, no problem. So just add fake nodes. So if we do that, BFS finds the shortest path, but there's a very good reason that we don't do that. And that's because if you remember, the running time of BFS was O of n plus m, and n is the number of nodes. So when we add these 999 fake nodes, we've basically really pumped up this n value. And in fact, we've also pumped up this m value because the original graph had 3 edges, and now the resulting graph has about 1,000 edges. And so that's why Dijkstra's is way better than this trick of using BFS and adding some fake nodes in between. But if we really needed to, you could solve shortest paths with BFS as well. So that concludes the discussion for the homework. Let's move on to some of the new material for today, which is this idea of totally unimodular constraint matrices. So let's recall the shortest path LP. The shortest path LP looks something like this. So minimize over y's sum of Cij, Yij, subject to everything going into S minus everything going out of S is equal to -1. Then we had something similar for T, and something similar for all other nodes. And then originally when we wrote this, we wrote something like this, that the Yij's had to be 0 or 1. But then we went in and we said you can actually drop that constraint and just say that the Yij's are bigger than or equal to 0. Well, to see why this is, let's first go back and rewrite this linear program in a method that's maybe quite familiar to you from your linear programming class. So it looks something like this. So minimize over y, c dot it with y, where y is now a vector and c is also a vector, subject to ay equals b, and y bigger than or equal to 0. So now A is a constraint matrix that comes out of these network flow constraints that we had up here. So let's see what the matrix A looks like. So first of all, the matrix A has m columns. There's one for each edge. And how do you know that? Because I know I have one y for each edge, and I have to multiply y times a. And it has n rows, one for each node. And that's because there's one of these constraints over here for each node. So for each node, the right-hand side is either -1, 1, or 0. Okay, so let's take a look at a particular graph and see what this A matrix might look like. So here's a particular graph. So 0, 1, 2, 3. And we said that the A matrix is going to have one column for each edge. So here's a column for 0, 1, a column for 1, 2, and a column for 2, 3. And we said it has one row for each node. So here's a row for 0, 1, 2, and 3. Okay, so this column for 0, 1 actually corresponds to the variable y01. So this variable is going to show up in some of these constraints and not others. And the only ones that it's going to show up in are the ones for node 0 and node 1. So when it shows up in the constraint for node 0, this edge is leaving node 0, so the coefficient of the variable y01 is going to be a -1. Similarly, because the edge is entering 1, the coefficient in the constraint for node 1 is going to be a +1. And this variable isn't going to show up in these other two constraints. So for the next column, it doesn't show up in the constraint for node 0. It shows up with a -1 coefficient in the constraint for node 1, a 1 coefficient in the constraint for node 2, and a 0 for 3. And the last one here is just 0, 0, -1 for leaving node 2, and 1 for entering node 3. So this graph that or this matrix that we've created has a special name. It's called the node arc incidence matrix. And the basic idea is that it has one node for every, one column for every arc, one row for every node, we put a -1 in row I for column ij. And that's because arc ij is leaving node I. So for node I, it's going to have a coefficient of -1. We're going to put a +1 in row j for column ij. So that's the node that this arc is entering, so it's going to appear positive over there. So it's really this constraint matrix that lets us drop the integer constraints. So let's see why that is. Basically, the constraint matrix has a special property that every column has exactly 1 +1 and 1 -1. But really, this property lets us show something else, that the determinant of every basis matrix of A is either +1 or -1. And I'm going to add this determinant fact with another fact, that every extreme point of the feasible region is a solution to something that looks like this. So by equals b, where b is a basis matrix, little b is the right-hand side of the constraints, and y hat over here is the extreme point. So this should be looking to you very familiar from linear programming, that we can basically get the extreme points as solutions to basically these equality systems where the matrix here is a basis matrix of the original. So there's one more piece to put this all together. And you might remember this piece from a previous class, which is that Cramer's rule from linear algebra tells us the following, that the jth coordinate of the extreme point, so this is the jth coordinate of the extreme point, is equal to the determinant of b with jth column replaced by little b over the determinant of b. So this is just a statement about solving linear systems like the one above. But this determinant right here, we know has values of either +1 or -1. And that's because B is a basis matrix of A, and every basis matrix has a determinant of either +1 or -1. This numerator, we would just have B with the jth column replaced by the right-hand side of the constraints. So let's recall what the right-hand side of these constraints look like. It looks like this. So this right-hand side has also exactly 1 +1, 1 -1, and all zeros otherwise. So it actually, this little b looks almost like a column of this big B, because the big B had columns that looked like they had exactly 1 +1 and 1 -1 and all zeros otherwise. So this top determinant is also either +1 or -1. But it could also happen that little b is linearly dependent on some of the columns in big B. So in that case, the top might end up being a 0. So putting this all together, putting the denominator and the numerator together, the value that the jth coordinate of the extreme point could have is either +1, -1, or 0. Now remember that originally we wanted the y's to be either +1s or -1s. And right now we're saying that if you solve the linear program with the simplex method, you're going to get an extreme point. And the extreme point can only have coordinates that are +1, -1, or 0. So we should be slightly worried about these -1s, but we're not really worried about them because we made sure that all the y's here have to be positive. And because of this positive constraint, we know that we can't get -1 out as an answer. So we can only get either a +1 or a 0 out as an answer, which is exactly what lets us drop these integer constraints. So now we know for a fact if we solve this linear program using simplex, the answers that we're going to get out have to be an extreme point, which means that all of its coordinates have to be +1s or -1s. So before we end this discussion, I have one more thing to point out. So when we created this LP, we were talking about sending one truck from S to T. But pretty soon we're going to want to send 5 trucks, let's say, from S to T. So if we send 5 trucks, these two numbers here would become something like a -5 and a 5. And if we go out over here, this determinant, when we replace B, isn't going to be either +1 or -1, but in general, it's going to be some kind of integer. And it's going to be just some kind of integer because B has all integers, big B also has all integers, so this determinant is just going to be some kind of integer. And when we divide it by +1 or -1, it's still going to give us integer extreme points. So pretty soon in class, we're going to start seeing different kinds of LPs that look like this. And their right-hand sides might not be so simple as for the shortest path one, but we know for a fact that the extreme points that we get out are going to be integers because this right-hand side, the B here, is also an integer. So that explains why we could do this magic with dropping the integer constraints for the shortest path problem in favor of just non-negativity constraints. And it concludes lecture for today. Thanks a lot for listening, and I'll see you all next time.